So in the previous module, we discussed the first postulate of quantum mechanics. As you remember, quantum mechanics is built upon a series of postulates. The first postulate is basically to know anything about the physical system, you have to know what the wave function of the system is. So the next question obviously is, how does one extract information from the system? To extract information from the system, you have to do measurements on the system. So what do you measure? Well, classically, in classical mechanics, we have many observables, right? What are observables? An observable is any quantity that you can figure out by doing an experiment on the system. Suppose if there is a particle, you can measure the particle's position, right? And if the particle is traveling, you can measure the particle's momentum. You can measure the angular momentum. You can measure the energy. So all these things constitute an observable of the system. An observable is something that you can do an experiment in a lab and figure out. Quantum mechanics basically tells you that these observables should be interpreted slightly differently in the quantum world. This leads us to the second postulate of quantum mechanics. This states that every classical observable, like position, momentum, angular momentum, energy, whatever it is, in quantum mechanics is represented by a corresponding Hermitian operator, Hermitian or self-adjoint operator. Okay, so in classical mechanics, then quantum mechanics, there is a difference. In classical mechanics, you have an observable called the position. In quantum mechanics, you have an X operator. In classical mechanics, you have an observable called momentum. In quantum mechanics, you have a momentum operator P. In classical mechanics, you can measure the total energy of the system, which is the kinetic energy plus the potential energy. In quantum mechanics, you have an energy operator. This energy operator has a special name, and this is called the Hamiltonian operator. Okay. Similarly, angular momentum is replaced by the corresponding angular momentum operator. Okay. Now, this might seem a little confusing in the beginning because, as I told you in the previous lecture, an operator by itself is meaningless. It has to act on something. So suppose if I want to measure the position of a quantum mechanical system, what do I do? Well, I have at my disposal the position operator, but the operator has to act on something. So this is where we tie postulate 1 and postulate 2. And the way you actually extract information about the system is to make this operator act on the wave function of the system in a certain way. What is the particular way in which X operator has to act on the wave function of the system? So we can understand what the position of the system is, or the momentum of the system is, or the energy of the particle is, and so on and so forth. So before in progress, please remind yourselves that quantum mechanics is a probabilistic theory. Excuse me. So remember that if you have some kind of a discrete probability distribution, as we discussed in the first lecture, suppose if we have, this is an aside, and this aside is important because we will tie the exact same concept to the quantum mechanical sense of extracting information. Remember that in the first lecture or second lecture, we discussed that there is some probability distribution with the ages of a bunch of people in a room. We call this some discrete probability distribution P of A. And we discussed that suppose if you have any function of A, then you can extract information like, what is the average value of this function f of A. And the way you calculate the average value of this quantity is by taking the sum over all the participants and multiplying it by the probability distribution. So this we called the average value, which we denote by some angular bracket. For example, the average age of all the people in the system would be the age of every guy multiplied by the probability of occurrence of this particular age. The average age square would be a square p of a, and so on and so forth. Okay. We can also extend this to a notion of a continuous probability distribution. So suppose if you have a continuous distribution or a discrete distribution like an age, continuous probability distribution, let us call this p of x, then you can actually measure the average value of any function f of x as simply, suppose if your probability distribution is valid from minus infinity to infinity, it is simply f of x weighted by the probability distribution integrated over the entire interval. Okay. All right. So the question remains, what is the average value of, since quantum mechanics is a probabilistic theory, we have to ask what the average values of positions and momenta and energies and things like that. So suppose if I ask that there is some quantum mechanical particle, we will do an explicit example as we go along. Suppose there is a quantum mechanical particle in some system, let us say a box of length L or something like that. What is the average value of the position of the particle? Okay. The specific question that we're asking is, what is the expectation value of the position operator x hat? Okay, so what is the rule in which we can compute this average values or expectation values? This is the rule that we have to calculate. The rule is basically this. The average value is simply whatever we want to calculate multiplied by the probability distribution integrated over the entire region in which we're interested in calculating this average. Okay. But what is the probability distribution in quantum mechanics? Well, we already know what the probability distribution in quantum mechanics is, because we already told you that the probability of finding a particle between x and x plus dx is basically psi of xt mod square dx. So this is equal to psi star psi dx. Okay. So the specific rule for calculating the average values in quantum mechanics is basically, so instead of I'll recall this equation 1, is basically equation 1 properly modified by taking the definition of probability into account. So this one subtlety here, so that we have to keep track of the average value of the position operator. Okay, calculated assuming that the system is described by some wave function psi of x is given by minus infinity to infinity psi star x x psi of x dx. Okay. Now, the way you calculate this probability is by sandwiching this operator between psi star and psi. Okay. The case of x, it doesn't matter, because x operator acting on psi of x is simply going to measure the position x times psi of x. So I can pull out this x here or put the x here, whatever it is. But suppose if I want to calculate the average value of operators that are dependent on things like ddx, I have to be a little careful and make sure that I sandwich this operator between psi star and psi. This basically is my rule for calculating the expectation value of operators in quantum mechanics. Okay. All right. So what does this mean? So let us work out a very simple example. So this famous example is called particle in a box. We will solve this in detail as we go along when we solve the Schrodinger equation. Basically, suppose if we have a particle confined to a region of space between, say, 0 and L, and this particle can only move either this way or this way. It cannot jump up and down. Okay. Basically, there is infinite potential barriers on these two ends, and the particle cannot escape this barrier. Okay, it cannot go outside this barrier because there is an infinite potential acting on the particle that x is equal to 0 and x is equal to L. So it can only go slide to the right or to the left. This quantum mechanical system, we will later find out, is described by a wave function that is given by square root of 2 over L sine n pi x over L. Okay. So the wave function can either be n can be 1, 2, blah, blah, blah. And it's not 0, of course. So sine pi x over L, sine 2 pi x over L, sine 3 pi x over L. So what are these states and what are the energies and things like that, we will understand later. But for now, just take this as a problem. Given this psi, now I can ask the question, for a particle confined to such a one-dimensional space, what is the average value of the position? The average value of the position I would calculate. In this case, I don't have to integrate from minus infinity to infinity. I should only integrate from 0 to L, because the particle cannot go beyond 0 or beyond L anyway. Psi star, in this case, psi is a real quantity, so psi star is the same as psi 2 over L sine n pi x over L times x times psi of x. So another quantity, square root of 2 over L sine n pi x over L dx. Okay. So for this particular example, the average value of position that I find is basically 2 over L integral 0 to L x sine square n pi x over L dx. Okay. So this I can write as 2 over L. There is multiple ways to solve this. I will solve it in a very routine, boring way. X sine square, I think, can be written as 1 minus cosine 2 n pi x over L over 2 dx. Right? Okay. So this is 2 divided by L. There is 2 integrations here. So there is a 1/2 factor that I can pull out. This is 0 to L x 1 minus cosine 2 n pi x over L dx. The first integration is x dx. The second integration is x cosine. So the x cosine part, I think, will add to 0, which you can verify yourselves. And this equation, this average value simply becomes 1 over L times x square over 2 between L and 0, which finally gives you L by 10, which seems like a perfectly reasonable answer, because the average the average position of the particle is not here, not towards 0, not towards L, but it's basically found midway. So this makes sense. So given a wave function, suppose if you're asked to calculate what the average position of the system is, of the particle is, you simply take psi star x psi and integrate this between whatever limits is applicable to the particular system that you're investigating. Okay. Of course, I can give you any function of x also. So what is the average value of, let us say, average value of some function of the x operator x hat? Okay, this could be x operator square plus 3 times x operator cubed. Not to worry, it is the exact same description. This function of the x operator is basically minus infinity to infinity psi star x f of x psi of x dx. That is all. Okay. So you should be conversant with this particular aspect. There is 2 operators that are of fundamental significance in quantum mechanics. There is, of course, many, but 2 that we will be studying for the time being. These are the position operator x hat that we've just talked about, and the momentum operator p hat. Okay. Many other operators can be understood as functions of x hat and p hat. So we should first understand what is x hat and p hat. Okay. So before we move on, let us talk briefly about what is the momentum operator p hat. momentum operator p hat. Okay. In quantum mechanics, in one dimension, the momentum operator p hat is given by minus I h bar d dx. It is a differential operator. Okay. This is a very important statement. So there is, so the first question is, why is the momentum operator minus I h bar d dx? There is various ways in which one can justify it. I'll justify it in a very simple way. Okay. So consider a free wave. Okay, a sinusoidal wave, a sine 2 pi x over lambda. Okay, I can write this wave as psi of x is a sine 2 pi x over lambda plus b cosine 2 pi x over lambda, or I can write this as a e to the I k x, where k is 2 pi over lambda. Okay, this k is called the wave vector. By the way, before h bar is called a reduced Planck's constant. It is Planck's constant h divided by 2 pi. This combination occurs a lot in physics, so it's given a special name for the reduced Planck's constant h bar. Okay. All right. Psi of x is a e to the I k x. Now, before I proceed, I will tell you, I'll warn you of one subtlety. You might be tempted to think that a free particle in quantum mechanics is basically a free wave and can be expressed as psi of x as a e to the I k x. This is not completely true. Okay, so in the case of a free particle is basically a particle upon which no force is acting, and it turns out that this system is actually quite complicated counterintuitively, and we have to work a little bit to understand what a free particle is and where is the particle and things like that. We will answer this question in detail as we go along. But for now, simply assume that this represents a free particle or a free wave. After all, de Broglie told us that all the particles have wave-like characteristics. So this is perfectly reasonable to assume. Okay. So this wave vector k is basically 2 pi over lambda. This is a sine 2 pi x over lambda plus b cosine 2 pi x over lambda. So let us act this p on this psi of x. What does this p acting on this psi of x gives us? The momentum, of course, operators need some functions to act on them. So I'm taking this particular wave function and acting it on the momentum operator. So this basically is minus IH bar d dx acting on psi of x. Okay, this is my momentum operator. So this is minus IH bar d dx acting on psi of x, which is a e to the I k x. A is of course a constant, so I can pull that out. And d dx acting on a to the I k x is basically I k e to the I k x. Okay. So if I group this properly, I have a minus I and an I together, that just gives me 1. So I can write this as h bar times k e to the I k x. But e to the I k x is precisely the wave function that I started with, psi of x. So this tells me that p times psi of x is h bar k times psi of x. In other words, psi of x is an eigenfunction of the p operator with eigenvalue h bar k. Okay. So we have accidentally stumbled upon, so basically we wanted to try and act this p on some wave function. And for this wave function, we took the wave function to be a free wave, which is a to the I k x. And it turns out that this wave is actually an eigenfunction of the p operator with eigenvalue h bar k. But what can this eigenvalue be? Well, this ties to postulate number 3, which we will move on to the next module. But let us actually investigate what this eigenvalue is h bar k. Well, what is h bar k? H bar is h over 2 pi, and k is, as we discussed, 2 pi divided by the wavelength. So this is h by lambda. What is this lambda? Well, assuming de Broglie's hypothesis, lambda is h by p, this can be written as h over h by p, which is just p. P is basically the momentum associated with the particle. So my P operator acting on the eigenfunction A to the ikx simply measures the momentum of the particle times psi of x. Okay. Now, as I said, many of the statements that I made are rather loose. I will actually make them more precise as we go along. So I just simply wanted to give you a taste of what the P operator acting on some functions would be. Now, it is not at all a guarantee that P acting on psi of x would give me something times psi of x for some random choice of psi of x. Okay. So we say that there are, if there is a system which is described by a wave function that is an eigenfunction of the P operator, then the eigenfunction of the P operator is such that P operator acting on the eigenfunction is the eigenvalue times the eigenfunction itself. Okay, so we will now turn this argument around and prove formally that the psi of x that we have chosen is indeed the eigenfunction of the P operator. To do that, let us construct the eigenvalue equation of P operator. Okay, how would you construct this eigenvalue equation? Well, P operator acting on some function of x equals some eigenvalue that I'm suggestively calling P times psi of x. Okay, let us plug in the definition of P in one-dimensional quantum mechanical system, which is minus IH bar ddx acting on psi of x equals P times psi of x. This is a simple first order differential equation which I can easily solve. D psi of x divided by psi of x equals 1 over minus I h bar times P psi of x. Okay, if I multiply the top and bottom of this by I get IP over h bar times psi of x. I can integrate this equation very easily. The left hand side basically gives me, sorry, not psi of x. I made it. This is an error. Dx. Okay. So I can integrate this equation in a straightforward fashion, and I get logarithm psi of x equals IP over h bar times d of x. Okay, and using the definition of the logarithm, I can write this as psi of x is basically some constant times e to the IP over h bar times x. Okay, and p over h bar, as we just found out over here, is basically k. Okay, I can equally well write this as a e to the ikx, where k is p over h bar, the wave vector. So a e to the ikx turns out to be an eigenfunction of the momentum operator. Okay, so suppose if I want to measure the suppose if I want to measure the average momentum of a system, what do I do? Well, if I'm lucky and if I'm in the eigen state of the momentum operator, then things become very easy. If not, things become only slightly more complicated. So let us actually take the same example as before. A particle confined to a small boundary of x length 0 to L. Okay. Instead of asking what is the average position of the particle, now I suppose I ask what is the average momentum of the particle. Well, how do I calculate this? It is the same rule as before, except that the operator that has to be sandwiched between psi star and psi is now the momentum operator. So this would become 0 to L psi star x p hat psi of x dx. Remember, initially it was x hat psi of x. X hat times psi of x is basically x times psi of x. But here we have p hat acting on psi of x. So again, this should be for the same choice of wave function. This would be 2 divided by L, 0 to L, sine n pi x over L minus I h bar t dx sine n pi x over L dx. Okay, so what is this? This is 2 over L minus I h bar 0 to L sine n pi x over L. ddx of sine n pi x over L is basically n pi over L cosine n pi x over L dx. So I can write this as 2 divided by L minus I h bar n pi divided by L. Sine times cosine is sine 2. So this is 1/2 0 to L sine 2 n pi x over L dx. And this, of course, is 0. Okay, so the average value of momentum for this particular state would be equal to 0. Okay, the average value of position is basically bang in the middle of the well. Okay, so given a wave function, you should be able to calculate the average value of operators with relative ease. Okay, so in the next module, we will go ahead and talk about certain intricacies associated with this eigenfunctions of the momentum operator and talk about how to normalize these wave functions properly. Okay, so for now, we will stop. The goal of this module was basically to give you a brief introduction to what the position and momentum operators are and how do you calculate expectation values or average values of the position and momentum of a particle or a given system given the wave function of the system.